So, let me ask you something. Is your laptop a genius? It's a wild question, but it gets to the very heart of what we're talking about today. What does it really mean for a machine to be intelligent? I mean, think about it. We all know computers are absolute monsters at calculating things. But does being able to crunch any number mean you can understand anything? Is that raw power the same thing as genuine insight? That's the big assumption we're going to tear apart in this explainer. All right, so here's our game plan. First, we're going to bust a huge myth that's been around since the dawn of computing. Then we'll introduce a totally new way to think about intelligence, a new theory of insight. We'll see it in action with a couple of really wild examples, build out a better framework from there, and finally, we'll get into why this isn't just theory and why it really matters for the future of AI. Okay, let's dive in. Our story starts with a concept that is, no joke, the bedrock of all computers you've ever used. But it's also the source of a pretty massive misunderstanding about intelligence. That concept is called Turing completeness. So what is it? Basically, if a system is Turing complete, it means it has the raw horsepower to do any calculation you can throw at it, as long as it has enough time and memory. It's all about potential. It tells us what a system can compute, but it says absolutely nothing about why it's doing it, how it's doing it, or what any of it means. And right there, that leads us straight to the myth we're here to bust. This idea that because a system, whether it's your laptop or the biggest large language model out there, is Turing complete, it must have everything it needs for true general intelligence. It's a huge leap, and as we're about to see, it's just not that simple. So if Turing completeness isn't the whole story, then what are we missing? Well, this is where a fascinating new framework comes in. It's called Intelligence Frame Theory, or IFT, and it gives us a much richer and, frankly, more useful way to think about all this. Now, this theory uses a fantastic metaphor that makes it all click. I want you to think of that raw computational power we just talked about, Turing completeness, as a blank canvas. The canvas is essential, right? It gives you the space, the raw capacity, the fundamental ability to create something. Without it, you're not painting anything. It's the foundation. But here's the kicker. A blank canvas isn't a masterpiece, is it? It's just unrealized potential. It's just sitting there. To actually make art, you need something active. You need the brushstrokes. And according to IFT, these are the 4 brushstrokes of insight. These are the active ingredients that intelligence needs: the ability to move information around, the dynamic of competition and collaboration that pushes a system to get better, the process of finding limits and creating structure, and then the big one, that eureka moment, that creative leap that generates something genuinely new. I know, that might still sound a bit abstract, so let's make it real. Let's look at a tale of 2 very different systems that puts this whole theory into razor-sharp focus. Okay, you gotta see this because this is where it gets wild. On the left, we have something called Rule 110. It's a simple little computer program, and it has been formally proven to be Turing complete. It's a universal computer. But guess what? It's totally inert. It shows 0 intelligent behavior. It's all canvas, no brush. Now on the right, we have a slime mold. Yeah, a literal blob of slime. It is not a computer. It is not Turing complete. And yet, it acts intelligently. It can solve mazes to find food. It transfers information with chemical signals. Its parts compete for resources. It finds its limits. It has the brushstrokes without being a universal canvas. So what is going on here? How can the official universal computer be dumb, but the slime is smart? Well, to solve this paradox, we have to zoom out and find a bigger, better framework.
And that new framework is built around a concept called General Transformational Sufficiency, or GTS. It's a system's ability to perform transformations, to solve problems using those brushstrokes of intelligence. And the really crucial part is that GTS doesn't care if the system is made of code or if it's made of cells and chemicals like a slime mold.
So the real hierarchy looks like this. The big category, the parent category, is GTS. That's General Problem Solving Ability. And Turing completeness, it's just one special symbolic type of GTS. It's a subset. It lives inside this much broader world that also includes smart, real-world systems like slime molds or ant colonies. This scorecard just lays it all out perfectly. Look, Rule 110, is it Turing complete? Yes. Does it use any of the intelligent tenets? No. so it's inert. Now the slime mold. Is it Turing complete? No. But look, it's covering the first three tenets. That's what we call proto-cognition. Then you get to an LLM. It's Turing complete, yes, but its intelligence is scaffolded. It relies on a human prompt to really get going. Only the human brain is shown here as what you'd call IFT complete. It has the canvas, and it has independent mastery of all four brushstrokes. Okay, so this is a really neat theory, but so what? Why does this distinction actually matter in the real world with all the AI development happening right now? Well, the stakes are massive.
It all comes down to something called the selector compression principle. It's a fancy name for a simple, powerful idea. Evolution is lazy. It always wants to find a shortcut. And real-world trial and error is slow, costly, and, often deadly. So advanced intelligence evolves to make insight cheaper and faster by doing the trial and error internally.
And this quote just nails it. The mind became the substrate of simulation. Instead of bodies having to physically try things out, minds could simulate ideas. Evolution went from this brute force machine to a super efficient ideation engine. It was a total game changer for life on Earth. And this brings us right back home to AI. This theory perfectly explains why just making the canvas bigger, just throwing more and more computing power at a problem, is never going to magically create genuine understanding. We need to build systems that have the dynamics of insight, not just the capacity for calculation. So I'll just leave you with this final question. As we move forward, as we build the next generation of AI, we have to ask ourselves, are we just building systems that can compute, or are we building systems that can truly discover? Because there is a world of difference between the two. Thanks for digging into this with me.